Better clench your cheeks, my dear friends, cause today we are going to... Our topic is the toxic catch rate bug, which affected both Ruby and Cypher, but was fixed in subsequent Gen 3 games. In order to tackle the issue, I have to explain some of the basics. I won't overdo it though, since it would easily cause the video to be way too long. It's also no big deal if you don't have any programming experience yet. You might still find it interesting to follow along and get a glimpse of the black magic happening in the background. The first thing we are going to talk about is actually a bit embarrassing for me, since I only learned about it while researching for this video. Even though I played this game since Gen 1 and have literal years of experience. As you probably already know, the health for Pokémon affects the chance of it being caught, but that's only one part of the equation to calculate it. One of the parameters are status conditions, and they have different multipliers depending on the exact affliction being present. If the target is asleep or frozen, the chance is doubled, while being poisoned, burned, paralyzed or barely poisoned will only boost it by 50%. With that being clarified, we can take a look at how exactly the game keeps track of its status effects. Internally, there's a differentiation between Pokémon being in the party or them being in boxes. Party members are described with a 100 byte long data structure, whereas the ones in the boxes only take up 80. This is due to the fact that the last 20 bytes in the structure can be calculated again by the previous 80 ones. This saves quite some space, which the cartridge actually had more than enough in the end anyway. If you're asking yourself why they didn't implement it the same way for party members if it saves so much space, then my best guess is either gaining some performance because the stats don't have to be computed every round when damage calculations are done, or just some regular Game Freak shenanigans. You never know. Starting at offset 80, 4 of the structure's bytes are used as flags for the status effects. Now I have to also tell you that I lied in my previous statement. Not all of the last 20 bytes of box Pokémon can be recomputed. The status effects and the current HP are simply discarded. You can even try it yourself. Just put one of your team members with a condition in a box and retrieve it again. Please also keep in mind that the GBA's processor operates in Little Endian. This means that the order of bytes in a data structure is reversed to what a human would define as normal. Now we have to make yet another important distinction. There are persistent effects, which we have already talked about, but also volatile ones, such as Leech Seed or Nightmare for example. Persistent effects will linger even after battle, whereas all volatile ones are cleared. And if I'm not mistaken, under normal circumstances, even when switching out during battle. At the start of a fight, those 4 bytes are copied to a temporary memory location, but only the flags for the persistent ones are synced with the original data structure. This means only a single out of 4 bytes are actually in use. That's what I call efficient programming. To be fair, it could also be that there were plans to introduce more persistent effects with Ruby and Sapphire, but they have been cancelled or downgraded to volatile ones. Finally, we can discuss the last bit of information before we jump into the code. The exact definition of the persistent flags. Sleep is represented with the lowest 3 bits, which means I can take a value between 0 and 7. This value is decremented every round, and once it reaches 0, the Pokémon wakes up. The other 5 bits are simple true-false flags, representing a single affliction each. For this video, we are only interested in the most significant bit, which is bad poison caused by toxic. When I started to research this glitch a very long time ago, I got tipped off with a link to the exact line of the faulty code in the Ruby decompilation project. I know, it sounds a little bit like cheating, but I only used that to quickly find an entry point where to start debugging the assembly code from. And just like initially assumed, the reason the problem occurs is because of a bit mask mistake. It left the most significant bit at 0, which means Pet poison is never considered when checking for status conditions, because I find it way more intriguing to debug the ROM instruction data. I figured out the starting address of the function this statement is in. When scrolling up, we can see that this function is called atkef_handle_ball_throw. Besides the master branch on GitHub with all the source files to build the ROM, there's also another branch called symbols. This branch contains symbol files, which map the name of the functions and such to the real address in memory. The ROM version I'm using is the English revision 1, so I open that file and show the contents. Search for the function name from before. The first column is the address in memory. Just to clarify that right from the get-go, the ROM addresses at the point of view of the processor have an additional offset added to them. Subtract this to get the real offset inside the ROM file itself. Now we can finally use a GBA emulator with debugging support. In my case, I used the developer version of NoCache GBA because it has breakpoint support and also shows the assembly instructions in a nice way. Before we start to step through the code, we clarify what we are actually looking for. The easiest way to find our final destination is looking for the bit masks. For sleep and freeze, it should be 27 in hex. And the bugged version of the other status conditions is 58 in hex, which actually should be D8. Okay, now that this is clear, let's set the breakpoint at the starting address and throw a ball to trigger it. What I did to make my life a lot easier was that I searched for some form of landmarks in the C code, which I know the assembly counterparts to. This way I can work towards the lines I'm really interested in small increments and know when I'm close by my real target. The first line with the breakpoint contains a push command, which saves the current register values to the stack and also sets the return address, so the processor can resume its previous operation at the end. This is normal for the start of a function and means the address we worked out before seems to be valid. Right after this instruction, we have the initialization of the ball multiplier variable with 0. I will not go into detail about each and every instruction, so be prepared to skip some steps from now on. Another super easy landmark are if statements, because they get translated into register comparisons and branch instructions. If you are familiar with x86 assembly, branch instructions in ARM are what you call jump over there. If I remember correctly at what I learned in school, back when dinosaurs roamed the earth, then C interprets everything unequal 0 as true. Looking at the assembly code, we can see the instruction is branch if equal, which means jump to the given address if the 0 register has been set, which in our case is true. Next is this line here, where two variables are ended in an if statement. This translates to an AND instruction, a register comparison and branch if equal. And just as before, we jump over the if block since the 0 register isn't set. Right after that we have the next block, which just behaves like the one before. No further commentary required. Now we enter the else block, jump over the first if statement with a branch if not equal instruction, as well as over the second one with a branch if higher. As we can see, the very next if statement is already the check for sleep and freeze, and the one after that, our goal. On this exact assembly instruction, I want to interject for a moment. It moves the value 58 into register R7, which is the value we are looking for, but we haven't passed the check for 27 yet, so this might not be the correct spot to fix the code. Just remember this line for later. A few lines later, we already reached the move and compare and branch if equal instructions for the 27 check. The line afterwards is the multiplication by 2, which gets translated into a logic shift left by 1. Unlike the check for 27, there is a direct move instruction for 58 when the evaluation takes place. And if you look closely, you can already see that register R7 is used for the end instruction. The same register I told you to remember about some lines above. The R4 register holds the status condition bits from the data structure and was used in both checks for 27 as well as 58. My first intention was to simply fix the value in the move instruction above, but this led to broken logic because it no longer loaded the status condition bits correctly into R4. The most probable cause is that simply by pure coincidence 5.8 is also some kind of offset when looking for the status condition data, but the compiler optimized the code to use the same register later for our end instruction, since the same value is required. Instead, I opted for a way more elegant and optimized solution. I add a move instruction before the end and drop the compare afterwards. That means I change 4 bytes in total and all code afterwards is kept at the same offsets, which is optimal for binary patches. This is possible since we call the end with the S option, which also sets the special register flags. If the end instruction results in a 0, the 0 register we evaluate for the branch if equal instruction is just set the very same way as if we compare a 4 against 0 later. To be honest, I am still not sure if those games are written in a higher language with bad compiler optimizations and programming in general, or if they just used handwritten assembly from their old spaghetti code before. Anyway, in the second column you can see the values for the end and compare assembly instructions. They are 40.3c and 2c00 respectively. We note those codes down as well as the address of the end instruction, so we know the offset where we have to change the values in the ROM file later. Since we also need the instruction code for the new move, we look at the R7 assignment from before. It's 2758 and should actually be 27D8. I close the emulator, open the ROM file in my hex editor of choice, HXD, and go to the offset we have written down. If you remember, we also have to subtract the CPU offset to get the real address inside the file. Go to that address and see both and compare instructions. You will also notice that the byte values have been reversed. That's because those values are written in Little Endian. I overwrite the compare instruction with the end one and then overwrite the original end with the new move. Done. Now it's time to test this fix. I already applied toxic to this enemy and threw a ball. The debugger holds at the breakpoint I set just inside the D8 block. Perfect. To be sure it has no side effects, I played for a while and everything was stable. I also looked at the code and traced the use of R7 in later parts. Its value is never used before it pops the original values back from the stack. So, all is good. Just out of curiosity, I also peeked at the code which the Emerald version implemented. They too inserted the move instruction before end, but also have the compare afterwards still. Basically, it does the same work, but uses slightly different registers in code. Seems like you managed to sit through this whole ordeal. Either you are very interested in coding, just like me, or you already fell asleep. If the latter is the case, sleep tight my friend, and stay hydrated. Anyway, finishing this video took me more than half a year, because for one part, I had to reset my whole PC because it was acting up, and on the other hand, because making such a detailed and technical video is a very daunting and work-intensive task. Certainly doesn't help that I'm a little perfectionist, and I can't bear doing a half-assed video. Also, since I work full-time on my real job, I often have neither time nor motivation to sit for hours on end editing. Sorry. Since this video was made over several months, the audio levels and quality is not consistent. It got better already, but I'm still working on a way to fine-tune it. With that being said, I hope you remember, never touch Game Freak code. Cheers.